Session A reads one account balance, 100. Session B reads the same row, 200. Both answers are correct. No backup was restored. No replica fell behind. And neither query is lying. Session A is looking through an older repeatable read snapshot, while Session B sees a committed update. PostgreSQL makes that possible by keeping versions of a row, then letting each query see the version allowed by its snapshot. That is multi-version concurrency control, MVCC. Most of us begin with a simpler picture. A table has one row for account 1. Its balance lives in one box. An update opens that box, erases 100, and writes 200 in the same place. But that model creates an ugly concurrency problem. What happens if a reader arrives while those bytes are changing? The database could make the reader wait, it could make the writer wait, or it could risk exposing a value that belongs to neither the old transaction nor the new one. PostgreSQL takes a different route. Keep the logical identity, account 1, but create a new physical row version. The original version v1 still contains 100. The update creates v2 with 200. They can coexist for a while inside the heap, which is PostgreSQL's table storage. A query does not simply ask, where is account 1? It effectively asks, which version of account 1 is visible to me? That distinction is the engine of the entire system. The primary key identifies the logical row. A physical version has a location called ctid. It also carries transaction metadata. Tuple xmin identifies the transaction that inserted that version. In this simple update, tuple xmax records the transaction that made the older version obsolete. These fields help Postgres decide whether a particular version belongs in a particular view of the database. Do not turn that into a shortcut formula. A non-zero xmax does not always mean deleted. It can also participate in row locking and multi-exacs. Visibility also accounts for commit status, the current transaction and command, sub-transactions, hint bits, and frozen transaction IDs. The useful model is not compare two numbers. It is, check who created this version, whether that work committed in time for my snapshot, and whether a change that superseded it is visible to me. Our update has one more useful property. The primary key, ID, does not change, and the new row easily fits on the same heap page. PostgreSQL can use a heap-only tuple update, usually called hot. The index keeps pointing to line pointer 1. v1's forward link points to v2 at line pointer 2. PostgreSQL can find the newer version without adding an identical key to the index. This exact chain is an optimization, not a promise for every update. Change an indexed value, or run out of room on the page, and the physical path can differ. Now add the snapshot lens. A snapshot is not a copy of the database. It is a compact description of transaction visibility at a moment in time, a lower boundary, an upper boundary, and transactions that were still in progress. Postgres uses that information with each tuple's metadata to decide which version the query may see. v1 and v2 can both be stored, but one lens lights v1 while a newer lens lights v2. The lifetime of that lens depends on the isolation level. Read committed is Postgres's default. Each command starts with a fresh snapshot, so two selects inside one transaction can see different committed data. A single select still gets a consistent view while it runs. Repeatable read behaves differently. Its snapshot is established by the first query or data changing statement, not merely by typing begin. Later selects in that transaction keep the same view, even after another transaction commits. That is why Session A can continue seeing 100, while Session B sees 200. Repeatable read gives a stable view, but an updating transaction can still receive a serialization failure and must be prepared to retry. Let's prove the model against Postgres 18.4. The database lives in a disposable Docker container with no published port, no external network, no host bind mount, and no persistent volume. The table has one row, ID 1, balance 100. AutoVacuum is disabled only for this tiny demonstration, so cleanup cannot race the camera. Pageinspect is installed for a super user-only look at the raw heap page. It is a debugging tool, not an application query pattern. Session A begins an explicitly labeled repeatable read transaction. Its first select returns. A sees balance 100 at ctid 0, 1. That first select establishes A's snapshot. Session B begins, updates the same logical row to 200, and returns. B wrote balance 200 at ctid 0, 2. The update completes even though A's ordinary read transaction remains open. B commits, then selects the row again. B sees 200 at 0, 2. Back in session A, the same select still returns 100 at 0, 1. This is not stale memory in the client, and it is not replica lag. Postgres still has both physical versions, and A's transaction-wide snapshot makes v1 the visible one. We can remove the friendly SQL abstraction and inspect the page. Pageinspect reports two normal physical versions. The first is the prior version and points forward to 0, 2. The second is the current version at 0, 2. We are not inventing transaction IDs or relying on a diagram. The two ctid values returned by the queries match the two versions on the heap page. This is where MVCC's greatest strength creates its operational cost. The old version cannot disappear while session A might still need it. Session B runs a standard vacuum with page skipping disabled for the demonstration. Vacuum finishes, but pageinspect still reports two physical versions. The update did not wait for A. Cleanup did. When session A commits, its old snapshot is released. Session B vacuums again. Now pageinspect reports one normal physical version. Line pointer 1 becomes a redirect, while line pointer 2 holds the surviving tuple. The index can still enter through its original line pointer and reach v2, but the obsolete tuple body is gone. Standard vacuum makes that space reusable inside the table. It does not normally shrink the operating system file. And vacuum is not the only time HOT chains can be pruned. Normal operations can remove versions that are certainly invisible to everyone. The lesson is the visibility horizon. Postgres must retain a version for as long as some valid snapshot could still see it. That is why an idle transaction can become expensive without blocking an update directly. Hold an old snapshot while a busy table changes, and obsolete versions accumulate behind the horizon. More versions mean more space, more cleanup work, and potentially more work for queries. MVCC trades read-write lock contention for version management. Healthy auto-vacuum and short intentional transactions are part of that bargain. One quick contrast makes the isolation rule visible. Session A starts a read-committed transaction and reads 200. Session B updates the balance to 300 and commits. Session A runs the same select again, still inside its transaction, and now reads 300. Same transaction, new command, new snapshot. Under repeatable read, that second select would have kept seeing the version visible to the first snapshot. MVCC also does not mean nothing ever blocks. Two writers that target the same row can wait on each other. Select for update deliberately takes a conflicting row lock. Some schema changes take stronger table locks. And repeatable read is not the same as serializable. Cross-row business rules can still produce a serialization anomaly, unless the application uses the right locks, or Postgres' serializable isolation and retries failures. So use this decision rule. Choose read committed when each statement may use the newest committed view available when that statement starts. Choose repeatable read when a transaction needs one coherent view across several reads, and keep that transaction short. Choose serializable when correctness depends on the combined effect of concurrent reads and writes matching some one-at-a-time order. And build retry handling either way when Postgres can reject a conflicting transaction. The durable MVCC model is 4 questions. What is the logical row? Which physical versions currently exist? Which snapshot is this query using? And which versions must remain because an active snapshot could still see them? Account 1 never became two logical rows. v1 and v2 were two physical histories of the same row. The snapshot lens chose the history each query could see. The HOT link kept the index path efficient, and vacuum reclaimed the past only after the final observer let it go.